Hello everyone. Today we are going to uncover one of the most astonishing hidden forces in our solar system. A force so gentle you could never feel it yet, so powerful that it can nudge entire mountains of rock, drifting through space, off their predicted paths. This is the Yarkovsky Effect, the invisible push from sunlight that quietly reshapes asteroid orbits, challenges our most precise calculations, and holds the key to keeping our planet safe from cosmic impacts. For decades, this phenomenon was a forgotten footnote in science, but today it stands at the heart of modern asteroid research, planetary defense, and our understanding of how small bodies evolve across millions of years. Let us journey through the discovery, the physics, the groundbreaking measurements, and the real-world importance of this tiny force that moves mountains in the void of space. Long before radar telescopes and deep space probes, a Polish-Russian civil engineer named Ivan Osipovich Yarkovsky made a revolutionary guess about cosmic motion. In the year 1900, he wrote a short pamphlet, far outside his professional work, building bridges and roads, suggesting that sunlight could exert a persistent tiny push on rotating objects traveling through space. At the time, astronomers focused almost entirely on gravity, the dominant force that guides planets, moons, and asteroids in their elliptical journeys. No one paid attention to a non-gravitational force proposed by an amateur scientist, and Yarkovsky's idea was nearly lost to history. It was only decades later that Estonian astronomer Ernst Pick rediscovered the pamphlet and brought this forgotten insight back to the scientific community. For nearly a century, the Yarkovsky effect remained a theoretical curiosity, too small to detect with the tools of the 20th century. But as our technology advanced, we realized this tiny force was not just real, it was critical to predicting where asteroids would be, hundreds, even thousands of years from now. So, what exactly is the Yarkovsky effect, and how can something as delicate as sunlight move a solid rock hundreds of meters across, or even kilometers over time? Let us break it down in simple, intuitive terms, no advanced physics degree required. Imagine a rocky asteroid spinning slowly as it orbits the sun, just like Earth spins, to create day and night. As the asteroid's surface faces the sun, it absorbs solar radiation, heating up the rock. But here is the key detail. Rock does not heat up or cool down instantly. There is a thermal lag. The morning side warms gradually, and the afternoon side holds heat longer, staying warmer than the morning half, even as the asteroid rotates. When that warm afternoon section turns away from the sun, it radiates that built-up heat back into space as infrared photons. Every photon carries a tiny amount of momentum, and when those photons shoot off the asteroid's surface, they create a faint, steady recoil force, like a microscopic rocket thruster, firing continuously in one direction. This uneven anisotropic emission of heat is not balanced across the asteroid, so it produces a net push that slowly alters the asteroid's orbital speed and path. That is, the Yarkovsky effect, in its simplest form: sunlight, in heat out, and a gentle but unrelenting push that changes orbits over centuries. There are two main parts of the Yarkovsky effect that govern how asteroids move: the diurnal component and the seasonal component. The diurnal effect, tied to the asteroid's daily rotation, is the stronger one for most fast-spinning asteroids. If an asteroid spins in the same direction it orbits the sun, a prograde rotator, the thermal recoil pushes it forward along its orbital path, speeding it up slightly and expanding its orbit outward, away from the sunday. If it spins backward, a retrograde rotator, the recoil pushes against its motion, slowing it down and pulling it into a tighter, closer orbit around the sunday. The seasonal effect, by contrast, comes from the asteroid's axial tilt and its yearly trip around the sun, dominating for slow rotators or asteroids with extreme tilts. Together, these two components create a consistent orbital drift that adds up year after year into massive changes that gravity alone can never explain. To grasp just how weak this force is, consider the numbers measured by NASA scientists. On asteroid 1999, RQ-36, later studied by the OSIRIS-REx mission, the peak Yarkovsky force is roughly half an ounce, about the weight of 3 small grapes here on Earth. That is, the total push, acting on a rock, half a kilometer wide, weighing hundreds of millions of tons. Let that sink in, a force you can barely hold in your hand, moving a mountain in space. For asteroid Bennu, one of the most studied near-Earth objects, the Yarkovsky effect shifts its orbital semi-major axis by about 284 meters every single year. Individually, each year's shift is tiny, but over a century, that becomes nearly 30 kilometers, enough to turn a harmless near miss into a potential threat, or vice versa. Before we could measure this effect, our long-term asteroid orbit predictions were off by thousands of kilometers, making it impossible to judge true impact risks accurately. The first direct detection of the Yarkovsky effect came in 2003, when NASA's Jet Propulsion Laboratory team tracked asteroid 6489 Golivka using high-precision radar. Over 12 years, the asteroid's orbit drifted 15 kilometers away from where gravitational calculations predicted it would be. The only explanation for that gap was the faint thermal push from sunlight. This discovery proved Yarkovsky's 100-year-old theory was correct and opened a new era in asteroid science. Later, the OSIRIS-REx mission took this measurement to an unprecedented level, mapping Bennu's surface, monitoring its rotation, and calculating its Yarkovsky drift with perfect precision, matching theoretical models exactly. Another famous case is Asteroid Apophis, once thought to pose a small impact risk in 2068. When scientists factored in its 170-meter annual Yarkovsky drift toward the Sun, they completely ruled out any impact danger for at least the next century, giving Earth a clear safety forecast thanks to understanding this tiny force. Why does this matter for all of us, not just astronomers? The answer is planetary defense. Earth is constantly visited by near-Earth asteroids, some large enough to cause regional destruction or global catastrophe. To protect our planet, we need to predict asteroid paths with perfect accuracy, decades, even centuries in advance. The Yarkovsky effect is the single most important non-gravitational force affecting asteroids smaller than 30 kilometers across the exact size range that poses the greatest threat to Earth. Without accounting for it, our impact risk calculations are unreliable. Every missing meter of drift in our models can become a life or death error when tracking a potentially hazardous asteroid. Beyond defense, the Yarkovsky effect helps us understand the history of our solar system. It explains how asteroids migrate from the main asteroid belt between Mars and Jupiter into near-Earth orbits, how meteoroids reach our planet, and how small bodies redistribute themselves across billions of years. It is a silent architect of the solar system's structure, shaping the skies we see today. Scientists are now exploring how we can use the Yarkovsky effect to our advantage, turning this natural force into a tool for asteroid deflection. One promising idea is to gently alter an asteroid's surface properties, for example, by painting part of it or changing its reflectivity to boost or reduce the Yarkovsky push, slowly steering a dangerous asteroid away from Earth long before it becomes a threat. This is not the explosive deflection you see in movies. It is a calm, precise, and sustainable method that uses the universe's own rules to protect us. It is a testament to how understanding the smallest forces in nature can give us the power to safeguard our entire planet. As we look out into the cosmos, we often focus on the most dramatic events, supernovas, black holes, colliding galaxies. But the Yarkovsky effect teaches us a profound lesson in space. Size and strength are not what matter most. Time and persistence do. A force too weak to measure in a day can reshape orbits over a century. A forgotten idea from a 19th century engineer can become the foundation of 21st century planetary safety. It reminds us that the universe is full of invisible wonders, waiting for us to look closer, think deeper, and appreciate the subtle forces that govern the stars and the rocks that travel between them. Every time we unlock one of these small secrets, we take another step toward mastering our place in the cosmos and protecting the only home we have ever known. The next time you see sunlight streaming through your window, remember that same light is reaching out across millions of miles, gently pushing asteroids through the dark, writing the story of our solar system, one photon at a time. The Yarkovsky effect is more than a scientific curiosity. It is a symbol of how every detail in nature matters, and how human curiosity can turn the tiniest clues into life-saving knowledge. Please like, comment, share, and subscribe to the channel